So let's recall what we talked about last time. So F is number field, and S is a finite set, finite set of places, including the places dividing L and infinity, and T is a subset. So I'm gonna just everything as before. So for a GFS, well, continuous, of course, always. M. So let's quickly recall these definitions. We define the M. The so-called this is relative cohomology. This is the global Galois group cohomology relative to the local Galois cohomology. Okay. So here I don't yet assume that T to contain all the places in dividing L and infinity. It's just sort of definition, and let H2 is IT Fs the cohomology of this. I is cohomology, of course. What is this? Okay. So last time we talked about two deformations. So we have this sort of deformation ring representing the deformation of this rho bar. Oh, maybe I should say rho bar absolutely reducible to start with. So let rho bar be an absolutely irreducible representation, and I can define this to be the deformation ring of rho bar with determinant chi and framed at T, right? And this ring admits a map from the tensor product of the local deformation ring. As before. And the theorem says that, okay, we can represent this global deformation ring as an algebra, or sort of, I guess, think of it as sort of something over the local deformation ring. And I'll write, then we can write R rho T bar frame T chi as, excuse me, I have to take this completion here. Maybe I'll just write this as local, R loc, with frame at T. So tensor product of all the completed tensor product of all the local deformations with some variables. Let me call xt, and then relations f1, fs, where T is. So for today, I'm going to write sort of H1. So the capital H1 is the sort of space of this cohomology, but I'm going to write a small lower letter for the dimension. Maybe sort of comma H I T of G F S M for its dimension. Okay, so I'm just going to write H 1 T G F S of the adjoint representation, and then S being the H2 T of G F S. So last time I proved this theorem for the sort of generator part T, and I didn't really prove it for the relation, but that's going to be an exercise. So today we're going to draw some consequences of this. let's see. So let's sort of again recall the Euler characteristic formula. So the Euler characteristic formula says that, to avoid trouble, let's assume that L is greater than or equal to 3, so that I don't have to worry about H3 in some sense. So the Euler characteristic of this representation is precisely the sum of all the Euler characteristics of the local ones, including the Archimedean ones. Okay, here I'm really taking the usual cohomology, but not the Tate cohomology. But then, because how I define this cohomology here, so this would imply that the Euler characteristic, if I take the relative cohomology for the global one relative to the local one for T in T, and maybe also assume that T contains all. Maybe just later. Just write this, okay? So I can look at the. I guess I can look at the relative Euler characteristic of this one. This is equal to should be equal to the Euler characteristic of the global one minus sum of the Euler characteristics of the local ones. And in other words, somehow I get sort of a sum. Yeah, that's good. With this equality, this Euler characteristic formula equality, so I get this is equal to the Euler characteristic of adjoint representation away from T. But if T contains already all places dividing L infinity, then this Euler characteristic is 0, because if the V is relatively prime to the of the residual characteristic of L, if V is relatively prime to L, then this local Euler characteristic is 0. That we've done many exercises on this, so this is just 0. But I want to make so this this will be the situation we're going to use in application. So let me make 2 comments. I'll prove in a bit. So let me make 2 facts. So this H0. So I'm going to assume this assumption that T contains all the places dividing L. This and it's H3. But because when you run this argument, you actually sum over H0, 1, 2, and 3. They're all 0. So that basically says that the H2 is the same as H1 in terms of dimension. Okay? So in other words, what we're doing here is that we're taking this sort of local frame deformation and we add T many variables. And then I divide it by the same number of relations. So a corollary of this, I'll prove this back in a minute. It's really simple, actually. So the corollary of this is that assume sort of rho bar absolutely irreducible, and this sort of T contains places, all places, maybe I should say, dividing L infinity. Then the Crew dimension of the global deformation ring, at T, is at least the Crew dimension of the local ones. Right, you add sort of T many variables and you divide by T many relations. Okay. But of course, I don't like to sort of count these frames all the time. So, in my personal way of writing, I'm writing this dimension of the global deformation ring is greater than or equal to sum of this dimension of these local ones. Or let me ask, it's the same thing actually. Of course, this can make sense, like if you're thinking it's in a stacky way. Okay. Another comment I want to make is that somehow we should really expect this to be an equality sometimes. I guess in at least in the good cases, this should be an equality. In the sense that a global deformation ring should have the same dimension as a local deformation ring. Right. And also, another comment I want to make is that it's crucial that T includes the Archimedes places. Because if you look at this equation here, the contribution of the Archimedes places is actually negative. We compute that the static dimension of the Archimedes deformation ring is -1 and -3 in the two cases of the two-dimensional representations, either odd or even. So that's something important, I guess. So I personally spend a lot of time sort of playing with the numbers so that somehow all these formulas come sort of more naturally instead of sort of giving a formula with lots of sort of terms. So I'm quite happy with this. So there's no extra sort of chunks of like +1 or plus some other numbers and stuff like that. It's a clean formula. Oh, let's prove the fact. I should not erase this. So let's do H0 for H0 is very easy. So H0 comes in here. So let's see. So by definition, this is rather rather by definition. This goes to the direct sum of. I don't even have to write that. Okay. So by definition, this H2 the relative Galois cohomology is so H0 goes to H0, and then this is H0 of the local ones. Okay. But this one already is 0. Because this is nothing but. So this is nothing but. Let's see. This is nothing but sort of the invariance of this representation under this Galois. Oh, sorry, no T here. It's just invariance of this. And we assume that rho bar is absolutely reducible, and we know that this, if it's an adjoint representation of this is just a constant F. Because this is just basically endomorphism by definition. It's an endomorphism of this rho bar. So this is F. But now you're removing the sort of the trace of this, which is removing from precisely this one-dimensional sum. So this is 0. So the reason I wrote circ is I'm removing the sort of the scalar matrices inside this endomorphism. So that's basically removing the origin invariance part. So what's left is 0. So that's why H2 is 0. So H3. H3 is sort of similar. Oh, wait. Oh, yeah, okay. Good. H3 is similar. So for H3, I want to first of all recall that there's a duality. Oh, I hope I got it right. Right, this is okay. Just me. So let's do H3. First of all, if S equals to T, so remember my T is sort of general, like T is a subset of S. If S equals to T, so I have this guy. And when we do global positive duality, one of the steps in the proof is that the dual of this H2 to 3 is isomorphic to H0 of GFS adjoint rho circ 1. The dual of this, maybe I should point out that somehow. The adjoint circ dual is just adjoint row bar circle. It's self-dual because, I mean, adjoint is, or rather, this is sort of the same thing as, maybe I prove it in an adjoint case. This is row tensor with row dual. This is by definition. So if you do it again, basically swapping two factors doesn't really change. And of course, trace part becomes, I don't know, maybe trace zero part becomes sort of the scalar part, etc. But it doesn't really matter. So self-dual is, I mean, this dual of this adjoint row bar 0 is just adjoint row bar 0. And they have trace by 1, but it doesn't really matter. In the same way, before it was somehow, this has no invariance. This basically sort of follows from the same argument, this has no invariance. Because it's irreducible, I think. Okay, so this handles case 1 s equals to t. If s doesn't equal to t, it should be clear. So nonetheless, let me give a proof. I don't know. This is a bit annoying. Let me try to prove this way. Let me prove a more general statement. So if I'm going to use it later, a claim. So I have this type of duality. I mean, this is sort of works for minus I and I, basically, right? So I want to claim that, roughly speaking, if I have a t here, or any m, okay, if I take the dual of this is isomorphic to the other side, 3 minus I. But then you have to do the complement of t in S. Okay. So we're doing this sort of the trivial case. We're using sort of the trivial case here, that if S equals to t, so this side is just 1, and on the other side you have this. So remember how this is defined. This is a cohomology of R gamma of G F S M star 1 relative to those in S but not in T. This is sort of taking maybe a clone of this. Okay, this minus 1. Okay, so if S minus t is trivial, it's empty, so you just don't have this term. So you're just return to this one. In other words, somehow like in this sort of duality, on this side, if you remove one v from the definition inside this relative cohomology, by taking the dual, we'll show how it shows up on the other side. Okay, so let's check this. This is not that difficult. However, I have to be a little careful here. I have to avoid certain cohomology. So let me think. Be cautious. Well, I have to. Sorry, this is not quite correct. I have to avoid the following cases. Just 1 second. I think I have to avoid I equals 1 if infinity belongs to t, or like, and I equals 2 if infinity, if this t contains an Archimedean component. Let me think. Just 1 sec. Just 1 sec. Shoot. So I did prepare this one. Maybe. In the case we consider, so you have to be a little bit careful. Maybe let me state it this way. So maybe not quite correct because of somehow this H0 of R of this M and H0 of R of M star 1. Okay, so we're going to be log of R, my notation. Okay. Sorry. Not quite correct. Because of these things, one has to be a little bit careful. But luckily, somehow, for all our applications we're going to talk about, this doesn't matter. Okay. Okay, so let's prove this. Let's pretending there's no problem like so. Or rather, let's pretending there's no problem issue from the Archimedean places. Because Archimedean place doesn't have sort of a duality. That's a bit of annoying. Okay, so let's see. How do we prove this? Well, this essentially follows from the following matching in some sense. Let's see. How do I do this? Okay, so what I want to do is I want to compare this with this. I want to compare these two cohomologies. So, how are they different? Let's see. Let's write it vertically. So I have R gamma. I write the T cohomology first. So I have GFS M. Right. The T cohomology, this goes to things in here. And the S cohomology sort of will look the same way. Hold on a second. I apologize. I should have done this earlier. Sorry. I think I got it wrong. I should use the quotient. I apologize. Okay. Sorry. I can map this thing into this complex and kill the part that's in S but not in T. So kill this sort of part that's not in S, not in T. So I get that cohomology. Right? So now I can take long exact sequence for this cohomology. So I get, let's see, I guess HI cubed of GFS M. This is sort of with local condition at S. This is with local condition at T. And by how things are defined, I think this is shift my minus one to the right. So I think this is going to be HI. So direct sum of T. And this will continue on to the I plus first. And so on and so forth. So when you have this sort of exact sequence of this complex, you would deduce immediately exact sequence as so. Now let's do the other side. I feel a little bit scared because somehow it's very likely to make a mistake here. I mean, it feels like I can either put this to the end or put it on this side. Only one of this is correct. At this moment, I'm betting on this one. The reason is, maybe why I didn't do it the other way is because if I do T here and S here, and then it goes to as kernel, you have this one. It's not a commutative diagram because this one, if I have something in here, it maps down and it maps to the right. It's not usually not 0. Whereas if you go this way, it's a 0. So when I read this, I should to say 0 goes to. So this has to be kind of in the sum, can't be in the quotient. If this goes in the quotient, you have something in here which definitely maps to 0 here. But if you go down this way, it's usually not 0. So this has to go into the sum object of the thing. There's several things of sort of placing this in the right place. So now let's do the other way. Talk about this definition of this space here. Okay, so let's match it up nicely. So over here, I want to put H3 minus I, GFS M dual 1, right? So that's where it's going to be duality isomorphism. So this is where, I guess, this is where the duality is going to be. So these two will be dual. So let's put it here first. And remember, there's a dual of one another. Okay? So bottom arrow, the bottom line will later on have a dual on them. So what I'm going to do is I want to sort of make the arrow to the left, and then when I take dual, all the arrow will come into the right. Okay? So arrow goes to this way. So this goes as H2 to 3 minus I of T of GFS M dual 1. Okay? By how this is defined, so this goes to the local one, so the direct sum of V in S minus T of H 3 minus I of GF V M dual 1. Right? So the kernel of this one is H2 right, 2 minus I of GF V M dual 1. Right? So now you clearly see that I made a mistake earlier because it doesn't match. It's supposed to match. So let's change that. So this has to be minus 1, and this has to be the 1. I'm claiming that this must be some sort of error earlier. I didn't do very well with the shift because when I write this down, it has to work. Otherwise, there's some problem with the math. Okay. Okay, you're going this way. Now you dualize everything. So now you see that vertically, these are all isomorphic. Okay, I lied a little bit why there's a map to start with. I guess why there's a map to start with. Oh, hold on a second. This is S in S minus T because the local condition is S minus T. So this has to be isomorphism. Okay. Again, this is ignoring all the sort of problems at sort of for this GR here. Okay, I should have spent some time to work that out because somehow if G is GR, then there's no duality here. Only the tail column has a duality, but the regular column doesn't have the duality. Anyways. Okay. So that checks sort of the this isomorphism. And okay, using this isomorphism, what is that we want to do? Okay, using this isomorphism, we see that I guess it's sort of clear already. I mean, like we see that somehow H3 T of GFS M dual is the same. And so I want to show this is 0, but then this dualizes to S minus T of GFS M twisted by 1. And this guy is 0. It's by sort of the same argument, basically. Okay. So that checks the dimension. Let me explain a little bit about why. So this maybe I should comment on this isomorphism here. This is this can be generalized to some sort of more general setting, in the sense that you should think of this as some relative cohomology. This is some other relative cohomology. For local state duality, the degree is like I versus 2 minus I. But somehow for the global relative Galois cohomology, the duality is between degree I and 3 minus I. And whatever the local condition you put here should serve the dual local condition on the other side. So that's the correct local, global, I guess, duality for relative cohomology. So it's in degree 3. Any questions about these? Okay, so let's see. So we'll talk about the relations later. So some of you asked me about what I guess what we're going for with this. So let me try to give an overview of the Taylor-Wells method. But this is very vague. So I'm going to call it Galois. So this is the Galois side of the patching argument. So let me quickly tell some story. So the following theorem is due to, I guess, Axler-Schmora, I think. K equals 2 and Deligne using Ital cohomology for k greater than or equal to 2, and Deligne-Serre handled the weight 1 case. That associated to each normalized cuspidal eigenform f q equals to sum of A and Qn of level usually called gamma naught n. There's an irreducible Galois representation. Call it rho f. The coefficients depend on your module form. Somehow your module form may not have coefficient in Q, so you have to throw in all these coefficients. So this is the sort of field extension of QP containing all ANs. And we can show this is a finite extension. So let's characterize this. We'll come back to this discussion of this later on, but I just want to sort of give you some sense of. So for every prime that does not divide at n, your Galois representation is unramified at L, and it's characterized by knowing the trace, or maybe the two eigenvalues of, or maybe, a characteristic polynomial of this rho f of this geometric Frobenius element is precisely x squared minus ALX plus L to the k minus 1. So basically the choice of Frobenius AL, and the determinant matrix is L to the k minus 1. Just some story, I'm not going to prove it now or talk about anything related to proof. But for what's important for Taylor-Wells method is the following rough form. So whatever I say here is very rough. So some technical assumptions. Not too bad. So suppose that I have two Galois representations, rho and rho prime, that are from. Let me write S. What is S? So S is all the prime dividing n. maybe I should put S here already. Oh, that's fine. I mean, because this representation is unramified at all the places not dividing n. So I put S to be all the primes dividing n and infinity. Okay. So suppose that I have two representations. Are two representations satisfying some natural conditions. In the sense that somehow they are, well, I guess they're unramified outside of the places in S, and at L, it has a particular, P dividing L. So, sorry. At L, there's an additional condition for it to satisfy. So I'm not going to talk about that condition at the moment. Just this. Then, suppose that I know rho is rho f for some modular form, a modular eigenform, as above, as on the other side, f of weight 2, say level n, gamma not n. And for us, one of the technical assumptions is the following: that rho bar being rho modulo the maximum idea of the coefficients is absolutely irreducible. So that we can talk about deformation rings in some sense. Then, this rho prime is also associated to a modular form. E is over QP, QL, excuse me, and that, the usual thing. The usual thing. Okay. So if you have some sort of two integral representations, integral coefficient representations, then you can, suppose one of them can be realized as sort of associated to some sort of eigenforms F, then rho prime will be also associated to some other eigenform F prime. Yes. So that's roughly what sort of the target theorem is. But how does it, so let me sort of give you some vague way of how this is done. Oh, so we assume this rho bar absolutely reducible. So here's how, roughly speaking, how the picture works. So let's write spec O here. This is coefficients. And I wanna look at sort of X rho bar in the sense that, let me draw the spec O first. Okay? So this is a coefficient, ZL. Okay, this is FL, and this is QL point, this is generic point, this is special point. Okay, every rho bar here, a point over the sort of special fiber. I think of geometrically. And somehow one of the rho, I think of it as sort of, the representation is sort of coefficient. Okay, I guess the rho is sort of the whole thing. Right? It's right. I mean, rho is sort of the rect2 module over O. Right? So it looks like so. And if I think it's sort of a deformation space, it'll be something over a spec of O. And in practice, maybe I should say in practice, here's a good thing to remember. Is that somehow this dimension of this X rho bar is roughly, if relative to O, the dimension is 0. Namely, it's roughly finite over the base. Okay? And I'm lying slightly a little bit. This is not maybe I should put a D here. There's some sort of conditions. I'll talk about the sort of condition deformation later on in the next lecture. So for a moment, let's ignore this issue, okay? So this is doesn't matter too much to our discussion today. So with this condition, this relative dimension is 0. Okay, so this is one of them is rho, and in the deformation I see another deformation. So rho prime. Maybe there's another one. Rho double prime. Okay, so maybe this rho bar will have 3 different lifts into K3 0. The way I draw this is that if 2 of them, goes along this line a little bit to the right, then rho and rho prime are more congruent than rho and rho double prime. So basically where they bifurcate is basically how much they sort of congruent to each other, modulo L. And what we're knowing here is that this rho does correspond to a modular form F. And I want to know whether this rho prime F corresponds to another F prime. So that's the idea. So one of the things that follows from this, this theorem of Ashker-Shimura, Lin and Lin-Serre, is that I can view somehow the space of modular forms. In some sense, I can even take a coefficient here, with ZL coefficient maybe, as a module over the deformation ring, maybe with a condition. In the sense that somehow, basically acting on this space, there's an element here representing the trace of the Frobenius that will act on this by the corresponding Heckel operator. Okay, so this can be thought of as sort of a function, a module over the deformation space. So this, this is sort of spec of the deformation space, and this sort of module on here. And the condition can be interpreted as this module has support along this line here, and I want to show that this module also has support over here. And also, of course, I have to show support over here as well for general purposes. So then the question is, what's the support of this thing? So basically, usually one can prove something like the support must be sort of the correct dimension. That's usually relatively easy to show. So therefore, the support must be of, if it covers this point, maybe roughly it will cover sort of the component. That's okay. But then somehow different components don't talk to each other. That's somehow the most difficult part of this, most sort of the biggest problem in this sort of modularity lifting world is somehow different components don't talk to each other. Well, of course, there's somehow a good case. Suppose that this X rho bar is somehow irreducible as a variety. So therefore, then the support will have to be, if it has the correct dimension, then it must be the whole thing. Then every point will be covered. Of course, we see this is not irreducible. I'm just saying, if it were irreducible, then there's no discussion. So Weil's idea is that somehow we're going to make this a little bit bigger in the following way. So Weil's idea is that somehow this global deformation ring is really difficult to control. We don't know much about it. But the local deformation ring, on the other hand, we can compute some of them at least. I guess you probably have tried some. We computed a couple last time. It takes some time to prove them, but somehow still, I think it's still manageable by hand. So here's somehow the modern understanding of what Weil's did. Weil's idea. Or rather, maybe I should say Taylor-Weil's-Keeson module. This is where I guess Keeson comes in. So Keeson think, or rather Weil's, I don't know. So I think of this sort of look. Okay, put a frame here, doesn't really matter. Put the frame at S, okay? And it has a maximal ideal, right, which is sort of the close point. And over this, I'm talking about sort of roughly same picture, but with sort of slightly higher dimension, with some sort of, when you pass from this one to the framed one, you just add some sort of dummy free variables. That doesn't really, anyways, just add some free variables, but somehow irreducible component doesn't change. So still you have some sort of rho bar here, and this guy is your spec, or maybe I should use spec for a technical reason you're going to see later. Doesn't really matter. This is alpha. You can talk about in terms of rings. Okay, frame at S chi. Okay, we're gonna change our point of view of this, in the sense that I want to look at the global deformation rate relative to the local deformation rate. The points of the local deformation rate are simpler. Let's put it this way. And the last proposition we proved, is that somehow the global one sits inside a sort of, I guess, a disk over the base. Maybe I should kind of draw a cone here. This cone is above of R log frame at S with some free variable. Okay, and this true global deformation ring is this thing modulo some relations. That's just a closed subset of this one. Okay. So Wild's idea is that, okay, let's release the deformation problem a little bit. So let's consider something called, let me write this. Rho bar, fixing a determinant. That doesn't really matter. Let's just put it in content here, that's okay. But I put in another Q, let's write Qn. It's a bunch of sets indexed by some integer n. So this is deformation of rho bar as a representation of, so originally I only allow ramification at the place in S, but now I allow it to ramify as some additional prime. Okay, I loosen up some place to allow it to be able to ramify. Then of course, obviously, I'm supposed to get some more choices. So I'm gonna get some more rows in some sense, right? And also maybe I should also mean for a finite set of places Qn. Okay. So therefore, this one, when you write it down again, R rho bar, R frame. What did I write? R log frame at S. I still use S. I don't relative to these Qn's. I just only relative to S. So that's why I developed this theory a little bit more general. I still want it to be. I still want this thing to sit within this relative disk I'm working with. I don't want it to grow out of the disk. Then I lose control. So I have some sort of fixed disk I want to work with. So I want to grow inside this disk. So this will be equal to x1 through x, still the same key, but modulo some other relations. You can show this still that many relations. But somehow the limit of this, whatever limit means, is 0. In the sense that when we allow, I guess, larger and larger primes in some sense, it will kind of fill up the entire disk in the limit sense. Okay? But what's the benefit of this? Or rather, maybe before to say the benefit of this, let me say that on the automorphic side, on the modular form side, we sort of do the same thing. So over here, I allow some verification at these Qn's. So on the modular form side, this will correspond to, I used different n's, maybe m. I'll go back to n later on. M. So many places have to change. So on the modular form side, I'm considering gamma nod n. Now I'm allowing verification at this point, so let me write, so this is basically if Qm equals to, I guess, Q1m to Q. In fact, the number of primes inside of here is always the same as this T here. So it's Q1m, QTm. Maybe I put gamma 1 level. It's just a sort of technical issue, don't worry about it. So I grow inside of this. So on the automotive side, I still have the same thing. So now I grow. Let me finish. So here's a miracle here. now, originally we're working with this sort of a single case. There might be many irreducible components. Now, how many irreducible components we have now? This is a relative disk to the local one. Very likely, the local one only have one irreducible component. And therefore, if we know that some rho, we have some lifts here, so that then somehow we know some point over here is some sort of modular, in the sense it's associated to a modular form. And we can bound the support of such module in terms of dimensions. And if the deformation space is irreducible, the support must be the whole thing. So therefore, what we prove is that somehow in some sense, some sort of limit of this R rho bar QM equals to the limit, some sort of limit, of the support of these modules. Sorry, the precise should be intersection with gamma 1, these Q, product of these Qs. We prove some sort of equality of the limits in some sense. And there's a mechanism to go back to each of the finite stage and show that because the limit side is equal, they're equal, then at each of the sort of initial stage, they're equal. So that's sort of a miracle. Okay, we'll take a break now, and after the break, we'll talk about how to choose these primes. Okay. So during the hello? Okay. So during the discussion, I think it's good to mention this toy model of this sort of limit. So in the sense that somehow I'm taking the, if we think it this way, one can pretend, for example, this global deformation ring as this quotient, right? So this quotient looks like sort of two-coordinate plane, a two-coordinate line, and then I'm enlarging this into this, which is some sort of a formal neighborhood, a little bit bigger neighborhood of this line, and then keep going. And then in the limit, you just get a spec of ZL, excuse me. ZL of x, y, comma 1. Right? So in the limit, if you take higher and higher power, it becomes ZL xy. So in some sense, this irreducible over here, if you talk about each Galois deformation ring, it may have sort of multiple irreducible component, but when you take sort of limit, there's only one irreducible component. Of course, with sort of higher dimension. But for as far as irreducible component, I guess our goal is to find the different irreducible components because they're not talking to each other. So that's a rough idea. So let me also mention two lies I did. First of all, I really need some sort of condition here. At the moment, we just sort of talk about plain, just no unconditioned deformation. But later on, we really need some condition, especially at the prime L. We'll do that, I guess, in a couple lectures. Another lie I did is this inverse limit. I'm really taking a bunch of primes. For different M, I'm taking actually different primes, QI. So in other words, there is no relation between sort of this R, this thing with QM, and this thing with QM plus 1. So there's no relation between them. There's no inverse system. Basically, what Wiles did is that, okay, a good analogy of this thing is kind of on a compact space, and he has infinite many points, or lots of points, then there must be a kind of a converging sequence, and choose that as limit. So therefore, this inverse limit is extremely non-canonical. Nonetheless, it somehow make the theory work. Okay, so that's the two comments. But for today, we're gonna sort of focusing on talking about the existence of these primes. In the sense that I want to grow my global deformation space inside a kind of a polydisk over the local deformation space and grow it. So let's do this. So let's do a hard zero. We've done the sorry part. Now let's come to the choice of. These are called Taylor-Wallace primes. Okay, theorem. So let, as before, I guess let F and S be as before. And I think I want L to be greater than or equal to 3 because for later application I do need L to be 3. Assume that this is absolutely irreducible, but I want it a little bit stronger than that. I wanted to, when you adjoin the following, when you adjoin square root of this plus or minus L, I mean depending on L modulo 4, with this plus or minus. If I understand correctly, this is I guess the quadratic field contained in the L cyclotomic extension. So assume that this, when you restrict to this, like this degree, the smaller Galois group is absolutely reducible. And of course, it's better to fix a determinant. So let's say determinant rho bar is just cyclotomic character. So I'll write T to be H1 as tilde. As we discussed earlier, same thing as this. By Euler characteristic formula. Then the theorem. Then we can find some primes. In other words, I have this sort of deformation picture as here, but then I want to grow inside this space. So then, for each n, there exists a finite set of places Qn I don't have to keep the n here, just write q. At the moment, I'm fixing the n. Okay, I'm not letting n to move. Later on, when we really talk about sort of the patching argument, we do let the n move. At the moment, let's not move n. Satisfying the following properties. First, for each v and q, the number of roughly speaking, these primes are all congruent to 1 mod p, but rather somehow the residual field, or sort of the number of elements in the residual field is congruent to 1 mod p, but it's mod p to the n. Very much congruent to 1 modulo p to the mod p to the n. And then this is unramified. Maybe I should say unramified. I guess somehow q is disjoint from S. Okay? So unramified place. And therefore I can talk about the Frobenius. And in this case, the Frobenius will have two eigenvectors, alpha v and supposedly qv, maybe qv inverse of this, okay? But I assume that the number of since qv is just this number of elements in kv, that's coming to 1 mod p to the n, so therefore this is just 1, so I can ignore it. Okay, this is modulo. Oh, I'm sorry, L. I apologize, L. In my mind, lots of time I'm using p as a coefficient. So okay, so q is coming to 1, so therefore this goes away. I want alpha this to be not equal to the same as the two forbidden eigenvalues are different. Remember when we talked about Taylor-Watts deformation problems, that's the condition I want. And the second condition is somehow related to this thing growing inside this disk. So this one way to see this is that this deformation ring, in the sense that I'm deforming rho bar as a representation of, as we get here, as a representation of this GFS allowing verification at S and Q, but I'm only taking frame at S. So this is a quotient of R frame log as before, with exactly the same variables we have over here. Okay, so that means we're growing inside of this. But in some sense, I'm adding in sort of T primes into this, sort of allowing more ramifications. I guess one can show that you can't do more than that. Let's keep this for just a bit to give you some sort of intuition. So let me make a quick remark before proving this. So the second condition here, there are different ways to write the second condition. One way to write this is somehow, basically by definition. Recall that there's a theorem saying that the number of generators you have to generate this thing over the local deformation ring is precisely the relative first cohomology. So just need that. This is also turns out to be also equivalent to the natural map. Or maybe we put it this way, so, excuse me. So maybe we think of it this way, so spec of R rho bar Q, maybe without the Q first. So let's look at sort of the original one. Over the log. And spec with the Q in here. They have the same tangent space. Okay, so they have the same tangent space basically. That's what I really want. I want to grow inside of this sort of this polydisk. I don't want to grow outside. If I grow outside somehow, I kind of lost control of the number of generators. And if we really think about what this translates in terms of tangent space description, it basically says it's a natural map of the tangent space of I guess the original one. You have the original one, you have the bigger one. Of course, the original tangent space will map to the bigger space tangent space. So this will definitely map to the bigger space tangent space, where you allow more ramification. This is an isomorphism. I'm just sort of translating the last condition in sort of different ways, or explaining what it means somehow really growing inside this polydisk. So the proof of this is essentially breaks up into two parts. Let me say this is one of the key theorems in Taylor-Well's sort of method, namely the existence of these primes. And after that, just a patching argument, and then conclude, basically. So that's why we spend so much time on understanding these deformation spaces and all these tangent spaces. So that's all used in here. I don't know how much time I have, but nonetheless, I will only prove it under assumption, slightly stronger assumption that rho bar of this Fs contains an SL2 FL for L greater than to the phi. That should simplify some of the arguments essentially, there are two steps of this proof. First is somehow reinterpret this condition, last condition here, in terms of another condition, which is easier to use Cherepov's density in the next step to find such primes. Okay? But then when you run Cherepov's density, it's very crucial of understanding the image of rho bar. If the rho bar has large image, it's very easy to use Cherepov's density. So I kind of assume this has a relatively large image. I guess if it doesn't have a large image, if the image doesn't only satisfy that condition, but also this one, there's some group theoretical argument, sort of working with sort of special cases, finite groups, that can be done to deal with that case. But I'm not going to talk about those cases, I guess. So yeah. Okay. So let me maybe first of all explain a little bit this equivalence in some sense. I guess somehow maybe explain, among other things, this injectivity. Of course, we know geometrically, we can see it very clearly in some sense. Somehow you're growing your deformation space. Right? So supposedly the tangent space should be an injection from the original tangent space to the later injected tangent space. But let me still kind of prove this. This is relatively easy, I guess. So let's prove this injectivity. It's just one diagram. I feel like I should train you to do more these type of diagrams. So okay, we have this cohomology, right? It's a relative cohomology. It represents sort of the kernel of essentially kernel of this. Maybe okay, fine. For the moment, let's just write this. I'm attempting to just drop this because it doesn't really matter. Drop the adjoint from the notation. It just takes up too much time to write. So let me do that. I'm going to drop this from the notation. Okay. To write less. Also important. And then going down. Sorry. Look, only local condition MS. So this goes to H1 of GFSQ, goes to B. And these are equal. There's a map down here. And similarly on this side you have. So these are all equal. So basically, I claim that this is injective over here. This injectivity is the first map in the restricted inflation exact sequence. Let me just write this down. So if I want to compute, so this I guess this is a quotient of this group, right? So therefore you have an inflation exact sequence goes from H1 of this invariance under whatever the kernel is. But of course the whole thing is invariant under that already. So this lives as a sub of this one and goes down to sort of H1 of the kernel of this group of this map into here with coefficient in the adjoint and then invariance and so such and such. But this is injective. So by 5 level, this is injective. So that at least somehow verifies that somehow we see geometrically this must be injected into here. And therefore, we know that this has dimension t. Then this guy has dimension t if and only if this is an isomorphism. So over here, so this guy has dimension t if and only this is an isomorphism. That's why this is equivalent to the first one. And basically the second one is just by definition equivalent to this one. Because this tangent space is precisely given by these, I guess, the dual of these things. But anyways, And that h1 equals t is is also equivalent to the t here. So that's why all these are equivalent. So, oh, sorry. Just one more thing. Just copy down. So what I need is this h2 to 1. Basically, they have the same dimension. This, right? Maybe GFS Q. That's equal to HS1 2 to G. So that's what I really need. Okay. Or rather, I want to prove. I guess I already know one direction. I guess I know this is bigger than that. So I want to know inequality this way somehow. Okay. Okay. So for the rest, I'm going to give an argument which is, I guess, more numerical. But one can turn it into a more like a diagram tracing and really showing that this injective is equal to something else. But I'm going to do the more numerical one. I think it's maybe easier to understand. Just a second. Oh, yeah, sorry. So recall that the Euler characteristics of these things are all zero. So therefore, h1 is equal to h2. In the two cases. So therefore, it's enough to show it for h2. For h2. Okay? And now I'm going to use the duality I discussed. For the relative Galois cohomology, a tilde 2S of GFS union Q. This dual is isomorphic to H1 relative to the cohomology of Q. Rho bar 1. And the other one being H tilde 2S. It's just literally H1. Because somehow this is the same thing. Somehow you're doing the S relative to all the sets of S here. So now we need to show these two have the same. I mean, originally I want to show H1 have the same dimension, and then by duality I want to show, but by Euler characteristic I need to show these two have the same dimension. Then by duality I need to show they have the same dimension. Okay. Now, let's do it this way. Hold on a sec. Let me draw a big diagram over here. Let me draw a big diagram to represent the two things. So for the H1 tilde Q, I just write down basically the definition of this. I kind of want, let's hold on a second. Actually, it's better to join. Sorry. If you're taking notes, leave some space up here. So by definition, this goes in here. This has a kernel, unfortunately. I didn't want it to have there, but anyways, it's there. H1, excuse me, H0. And this one has a sub. I mean, like but this sub is 0. I mean, this sub is basically a row bar 1 invariant under the global Gauss group. But this is absolutely reducible, so it's 0. Doesn't matter. So this is what one of the term here is. This is the top one here. The bottom one is really nice. It's just a clean cohomology. But the only difference is somehow this cohomology you allow ramification at S, but you don't allow ramification at Q. So it doesn't quite compare this directly. So I have to compare that with the one basically using this map here. Remember, the H1 of GFS maps to H1 of F, allowing ramifications. This is a restriction inflation exact sequence. This is the inflation part. So this, what I have by inflation. You should know that I don't like to use inflation restriction kind of language, but anyways. What's the co-kernel of this one? I mean, somehow, naively speaking, I mean, you have some class. So this is some sort of a commutative class in terms of unramified at places in Q, because the group is unramified. And you inflate it to allow some ramification. How do you go back? You wanted to go to the place of the thing that measures ramification. So this goes to of H1 of inertial subgroup of IQ of this. Okay? I'll explain why this is exact in a bit. You should think somehow, or I mean, forget about this H1. Think of this as a hum. Because H1, when it's a trivial action, this is just a hum, right? You're humming this scalar representation into the space, right? If it's restricted to the inertial subgroup is trivial, then it must factor through the part that's unramified. And in fact, that's how it's going to be proved. I'll show this right here. So prove the exactness here. I actually don't have a good proof. So let me do it on a chain complex level. Okay? Sorry. I don't have a good proof. So let's say. So basically, I mean if you have something in here, you inflate, and the way you inflate is basically, you take, it's just basically send CG to CG where you project this down here, right? And this is a restriction, right? Then inertial group maps trivially down here. So if you have a class here, maps here, and the maps over here must be 0. But then you have to show that anything in here, in the co-cycle here, maps over there to be 0. It must come from things over here. Okay. So let's say I have some sort of chain. I have some sort of co-cycle in H1 of GF. To be honest, I don't quite like this proof, but anyways, I have to say. Now, what do we know? Such that the restriction of this map, of this, is 0. Okay? Let's rewrite this a little bit. If it's H1, it's difficult to work with. But we know that the initial group really acts trivially on this representation because rho bar is unrelated at Q. So this acts trivially here. If it acts trivially here, this H1 is nothing but just a hop. That's group, a continuous group. I mean, always continuous. Right. So if the group acts trivially on the module, then automatically this H1 is just a hop. It's group homomorphism. Somehow the boundary map for the group cohomology is trivial. So that means if you restrict it to be 0, that means that for every gamma in the initial group QV, C of this gamma is really just 0. I think of the C as a map from the Galois group to joint. I think of it as the standard, co-cycle map. But if I have some element in this initial group, for V and Q, initial subgroup, then the C of this gamma is 0. And then moreover, okay, so now if I have C of, now for any G in GFSQ, then C of G gamma must be equal to, maybe gamma G is equal to C gamma plus gamma CG, right? But we know that C gamma is 0, and then gamma acts trivially on this space. So this is just the same thing as CG. In some sense, it doesn't depend on this coset on the side you quotient by some I. For all the i's, you can quotient on the left. And I think for some other arguments, you can show that this is even true for all the conjugates of this I. Somehow, but we know that GFS is a quotient of GFS unique by essentially conjugates of IB, B, and Q. So that means that somehow whenever you write CG, it only depends on the quotient. So therefore it must come from here. That's the idea of how this is done. And this is already in general. So whenever you have a module here, you have that for H1. Okay. Now I have this map. This is the same thing. And this is a natural map restriction. The Galois group back into that. And the kernel of this map is, this is a local Galois cohomology calculation. So it's a local Galois cohomology mapping to the singular part in some sense. So the kernel is precisely H1 of the finite field cohomology. Right. So now I want to maybe just count. Let's see. What should I do? So I have this thing here. This is a submodule of this one. Basically, I want to kind of create some sort of snake lemma kind of situation. Okay, you'll have to play with the diagram. So this is a submodule of that one. So maybe let's quotient this over. Okay. So this quotient by this thing. Now this becomes 0, goes to that. Okay? That doesn't change much. Now because this is, when I'm in this situation, now these two vertical maps will give me a map down here. And this being injective implies this being injective. I guess I actually don't know quite a good way to explain this. One way to see this, I want to see, for example, I wanted to see the snake lemma in the following way. So I have two vertical exact sequences. So, okay. So this is the exact sequence. 0 goes to this, equals to this, goes to 0. 0 goes to the something here, something. This doesn't have to be 0. If you want a snake lemma, you don't need to go to 0. Then the snake lemma goes as, so you have, let's see. So you have this term is, the kernel of this is 0, goes to this term, and then snake. Suppose to go to the co-kernel of this one, which is just this term, because 0 goes there. I don't know. I mean, maybe there are ways to define it. You can do this, and then pull up. The equality goes up, and then goes here. You can do zigzag. I mean, that's the same thing as snake, anyways. Anyway, you have this such a map like so, and this is exact in the sense of this goes to this, goes to this, goes to that is exact. I don't know. It's one way to do this. Okay, let's count the dimension. Right. Maybe I should start from the very beginning. So, okay, so these ones are. Remember, these are all t. So at least somehow this. So we know that HS1 tutor, TFS, the cohomology I started out with is t, and this is the same thing as H2. So these are all t-dimensional. And taking the dual, still t-dimensional. Okay? So basically, I know this dimension. So this guy has dimension t. And I want to know this one has dimension t or not. I mean, I know one of the dimension. I just want to show the other one has the dimension t. So putting it in this picture here, I actually know this guy has dimension t. And what about the thing I quotient out by? Let's check. Let's check this dimension. So what is this? Remember when I have to take the Q to satisfy the first condition, which is sort of number of elements in KV is you probably can't see it. It's congruent 1 modulo L. Actually L to the N, very big N. It doesn't really matter. And also the row bar of Frobenius V is alpha V bar inverse. Okay? So then what is the R joint of row bar circ and 1? This is alpha, basically this tensor with dual, and you remove an eigenvalue 1. And also, maybe I should also say that because my number of elements in the radial field is common to 1 mod L, so this twist is it's the same thing as without the twist, because cyclotomic character is trivial. The cyclotomic character will send the Frobenius to this Q or Q inverse, but it's common to 1, so it's just trivial. So it's the same thing as this one. This R-joint representation has sort of 4. Without the circ, the 4 eigenvalues are the ratios, alpha B bar mod, alpha B bar inverse, and the quotient the other way, and 2 ones. And now if I do circ, I remove one of the trivial ones. I get these 3. And our assumption requires that this is not 1. This is not 1. So that means when I take H0 of this representation, I pick out precisely this eigenspace. So for each V we have over here, we have a 1-dimensional space over here. Altogether, this is t-dimensional. Okay. So I guess the quotient is 0, it turns out. But I guess this quotient turns out to be, because it's t-dimensional here, and it's a genuine quotient, so it gets 0. Okay, fine. But I guess somehow my discussion works for a case when Q is a little bit smaller. So it doesn't have to be t. Anyways. So I guess somehow it turns out this quotient is 0. By dimension count. Will be 0. Okay? Now it comes down to this embedding into this guy. And what is this H1 here? So this is H1 of the residue field. Residue field H1 is the same thing as this adjoint modulo Frobenius minus 1 times that, right? Again, you're counting how many eigenvalues, which is 1. So that's precisely just this 1 here. Maybe I should write. So what is the H1 of the red? So this is adjoint. Quotient by the Frobenius action. Times adjoint. So this is basically killing all the eigenspaces where the Frobenius doesn't act trivially. And this adjoint circ 1, there's only one Frobenius eigenvalue being 1. Others being not 1. So left with one dimensional for each v. So this guy is t-dimensional. In other words, we're left to show. I'm sorry. I think I missed some mistake. Hold on a second. Sorry. I made a mistake. Sorry. Sorry. I don't know that dimension. Sorry, I know this dimension. My bad. So this is dimension t. Okay. Excuse me. This is dimension t. I want to show this one has dimension t. My bad. Sorry. I know this dimension. This dimension t. It maps to a t-dimensional space. And I want to show the kernel. I want to show this guy has dimension t. But already this is quotient by some t-dimensional thingy. So basically I want to show this quotient to 0. That's equivalent to show this is injected. Sorry, confused. At the end of the day, both of them have to have dimension t anyway, so I'm confused. Think about it. So start over here. So we show that this guy, the FS1, has dimension t, which is this guy has dimension t. Okay? And I want to show the top one has dimension t without a quotient. Now this is already kind of quotient out by a t-dimensional guy. So basically I want to show after quotient this guy becomes 0. Okay. Now I have a t-dimensional thing mapping along this map to a t-dimensional thing. And I want to show the kernel of this one, namely this quotient is 0. So equivalent, I want to show this is injected. Right. I'll leave it as is for you to think. Basically, I want to show the snake map is injective. For the dimension reasons, it must at the same time be an isomorphism, but I don't care. Oh, sorry. Or I guess not need to show, but need to find Q such that basically that's what I want to do. It's a little. Let me make a remark that somehow. Remember that earlier I have sort of injectivity somewhere. I want to show it's surjective. One can use some more algebraical proof way to show that that's actually equivalent to this being injective, without going through these sort of numerical equalities. But I think with a little bit more diagram to chase. So I decided that maybe I'll just sort of use a little numerics to reduce the case. Anyways. So 5 minutes. Are there any questions about these? It's a long diagram chasing. Now, once we reduce this to this case, it becomes sort of some sort of Chebyshev density argument. I have a choice of whether I do this in 5 minutes or I leave it to the next lecture. Maybe I should leave it to the next lecture. Are there any questions about this? So it's right. Maybe I'll leave that to the next lecture to actually prove that we can find it. It's a Chebyshev density argument to show that this. Essentially, what you want to show is that for every class C in here, you can find. So basically, you want to show that find some good V such that the restriction of this class, or rather, I'm sorry, the restriction to KB, my bad, the residual class. So such that basically C, well, maybe write down what I need to prove, and then I'll kind of stop. Essentially, I need to show that for every class C not 0 in H1 of GFS, I can find a place V, not in S, of course, such that three things. First, number of elements in the residue field is common to 1 more L to the N. Secondly, for a row bar of Frobenius V has distinct eigenvalue. And thirdly, I want C. I mean, this class here does not belong to the thing you're quotient down by. Does not belong to sort of Frobenius of V minus 1 times this adjoint representation. I mean, I could have put this circ 1 here for the cyclotomic twist, but somehow, I guess because for the residual Gauss representation, the cyclotomic twist is trivial because of the first condition. So next time I'm going to somehow do this, I guess. Let me quickly make a remark that, of course, for each C, I can choose some sort of V like so. Now I can take direct sum of all of them. So then I get some sort of injective map from this going into here. And of course, I throw out a bunch of things I don't use so that I get an isomorph. Because this guy is T-dimensional. I exactly need T elements in here. I exactly need T summons here so that I build an isomorphism. Okay. Good, maybe I'll just end here early.